Yeah,
Good morning.
yeah.
You
Okay.
ready?
All right.
Okay. All right. Good morning, good
Okay.
afternoon, good evening, wherever you are. So, welcome to the third P2X webinar series. And this event, before we start with anything, I would like to mention our sponsors. So, this event is funded by the Royal Academy of Engineering in the UK. And the purpose of this is to spread the word and to build a community around the powers to X um, research theme, meaning that we want to turn power into something useful. It doesn't have to be electricity all the time, but it can be chemicals. It can be using power to do convert carbon dioxide to something to green chemicals. And this is what we're gonna hear about it today. And today we got a great friend of mine, Dr. Phong, whom I met back in Japan in Tohoku University, and he then moved to France to finish his PhD, and now he is a postdoc at the Collège de France in CNRS. And today the topic will be copper-based electrocatalysts for CO2 valorization at industrially relevant conditions. So this is a very good opportunity to see the research gap between the research scale, the lab scale, and try to reach what is commercially viable. So without further ado, let me welcome you and give you the floor, Dr. Pong.
All right. Thank you very much, Shannon. It's my pleasure to give a talk today for you guys. Yeah. Back to the time. Yes. It's true that I was at the same university with Dr. Shannon in Japan. At the time, I'm in my lab, and Shannon lab was just like few steps from each other, and I met him quite a lot of times. Yeah, yeah. At that time, my research when I was in the master was about the photocatalyst for water splitting to synthesize the hydrogen. And yeah, at that time I was just working on the design of the photocatalyst and the solar energy. Yeah, but then yeah, I decided for my PhD and postdoc, I moved to France at Collège de France and focus on different copper-based electrocatalysts for CO and CO2 reductions. But firstly, we need to know why we have to work on CO2 reductions. Okay, so as Shannon just mentions, we can store the energy or we can make the chemical in different ways, either by solar energy, wind energy, or even some carbon neutral electricity. Especially in France, since the source of nuclear electricity is very abundant. This is why these countries focus a lot on the use of carbon neutral electricity to do other things. So one of the way is that they just they absorb the CO2 in the industrial scale and then try to convert it by the method of electrical electrochemical method. Okay, and in these things, they can utilize a thing called the electrolyzers, and then by this way we can obtain different high value chemicals, for example, formic acid or carbon monoxide. Uh, the formic acid can be utilized for further chemical reactions to synthesize different fuel. For example, methanol by the thermocatalysis. Even carbon monoxide is also a good chemical feedstock. Okay, and so by this way, okay, you see by using the carbon neutral electricity, convert the CO2 waste from the plants or anything, and you can utilize the high value chemical, and then back to then you can have a thing called the carbon cycle to get it close. Okay, and okay, why we have to work on CO reductions? of course, in the atmosphere or in any chemical processes in the industry, we don't have that much CO. And the most abundant waste is the CO2. But why we work on CO? Okay, well, firstly, considering the chemical point of view, in fact, CO2, okay, is firstly reduced into C1 products. So we have three different types of C1 products can be obtained from CO2 reductions. The first thing is formic acid. The second thing is CO, and the last thing is methane. Okay, but from CO, it's there has been like uh, quite a lot of research working on CO reduction. So from the CO reduction, we can obtain different multiple carbon products, for example, ethylene, ethanol, n-propanol, and acetic acid. And also, I have to note that these multi-carbon products are usually very difficult to synthesize uh, from the direct CO2 reductions at at very high efficiency. Because imagine if you have to combine long chain products, it means you have to bind a lot of CO2 or molecule together. And also another thing is that look at this alcohol. It is very difficult to get the oxygen molecule or the oxygen species into the carbon chain and make it stable. And also at high efficiency is very challenging as well at the point of thermodynamic. On the other things is that in the research of CO2 reductions, we usually utilize alkaline electrolyte. Why? Because we would like to minimize the hydrogen evaporation reactions, which is a competing reactions with the CO2 reduction. Of course, getting hydrogen from the electrolysis is very nice as well. But in this case, we care more about the CO2. We don't want the hydrogen. Okay. So this is why usually we work with very high pH to avoid these unwanted reactions. Another point is that usually considering the electrolyte, the alkali electrolyte give much lower voltage compared to the neutral or the acidic uh, electrolyte, thanks to the high conductivity of the alkali electrolyte. But at the same time, using alkali electrolyte with CO2, you have these spontaneous reactions, which is called the carbonate formations from CO2. And since the solubility of the bicarbonate salt or the carbonate salt is very low in the aqueous solutions, these type of things can accumulate the salt, which make the cells resistance very high, and then we waste much energy to get the reactions happen. And also, this is also consume a lot of CO2 reagents, which means okay, we spend a lot of electricity just to get CO2 into carbonate, and we don't want that at all. On the other hand, CO is it is not active in the alkaline condition because CO doesn't react with the hydroxyl group as you show here. This is why I think in the last 8 or 7 years, there has been numerous reports about the work of CO reductions into different multi-carbon products. Okay, and yeah, yes, back to the questions again. Okay, if you want to make them work at the industrial scale, what do we need? Okay, the first thing that we need a good device to convert the CO2 into CO at first. Okay, to get enough amount of CO. So okay, like 6 years ago, there was there's a report showing that using a device called SOEC, which means the solid oxide electrochemical cell. So this device utilizes at the same time the heat and electricity together, and this device can convert the CO2 into CO with very high faradaic efficiency, like almost 100%. So for those who are not familiar with electrochemical reactions, so Fick efficiency means that this means the amount of electrons utilized to make the products over the amount of electrons you apply to the system. Okay, of course you can check it later to get more clear point of view. Okay, and then by using this about the amount of CO, we can just put it to the next electrolyzer, which is called flow cell. Maybe someone can you just mute? Okay, good. Okay, using the flow cell, okay, we can also convert the CO into the different things, or I mean, either n-propanol, ethylene, or ethanol. Okay, so what is a flow cell? Okay, I will talk about this because it's a very interesting concept as well, and it has been like founded to target the industrial condition. Okay, so in the flow cell, this device is on the fundamentally it is very similar to the H cell or any electrochemical cell. It contains like the membrane, electrolyte, electrode, reference electrode or counter electrode. Okay, but the the special point is that this flow cell utilize a thing called gas diffusion layer and coated by the catalyst. So this gas diffusion layer contains the carbon porous structure to make the good conductivity, and on the back side it is also coated with the PTFE. So the role of the PTFE here is to improve the hydrophobicity of the electrode. By that, the electrode can be more hydrophobic, which can minimize the rate of the hydrogen evolution reactions, which is mainly come from the electrolyte. Okay, and on the right side we can flow CO, either CO or CO2. But in this case, I work with CO, and then for the gas phase, usually we get ethylene as a main product, and hydrogen. Of course, we always get hydrogen, but it's just the question of how much we get. Okay, and then in the liquid phase, we have the ethanol and propanol acetic acid, and those products are usually the main products from the CO reductions. Okay, and in between the cell, we also have an ion exchange membrane. It can be either anion exchange membrane, cation exchange membrane like naphthalene or anything. Okay, to exchange the ions between the two sides, the cell compartment. And in the anode, we have the water oxidations to make oxygen. And this reaction is to balance the charge, okay, and also the ions between the two compartments of the cell, okay. And usually in our case, since we work with alkali conditions, the anode we use is nickel form. But in other cases, for example, people might work in neutral pH or acidic pH. They might go to iridium oxide or other things. But this field of research is also very interesting, and maybe it's also the thing you can consider later. But today I will just focus on the Catholic part, okay, which is my project since the PhD and postdoc. Okay, so the things, the important thing here is that with the gas diffusion layer, we can also achieve a thing called triple phase boundary. So what it is? So triple phase boundary means the phase between the catalyst, the input gas, and also the electrolyte. And here, since okay, we make this boundary, we can run the reactions at very high kinetics, and usually these cells allow us to go up to like ampere level current density, which is very how to say demanded for the industrial applications, because in industry we want a very large amount of product, and also by very at a very short time. So it means you need to get a very high kinetic, and also you also need to reduce the resistance of the electrolyzer. And yeah, to compare, so imagine in back to the traditional design, which is the H cell. What we need to do is that we have to saturate the electrolyte by the CO2 or CO, but it takes a lot of time, and also the solubility of CO2 or CO in aqueous solution is not that good. Okay. Okay, and yeah, in this research, I focus on the flow cell, okay, and the catalyst design. Okay, so considering the catalyst, what we need to use for the CO reduction. So yeah, there's has been a lot of research about this. So people try different method in the periodic table, and we found, okay, back to the year to 1975 or something, in Japan. In fact, it was Hori, okay, Professor Hori. He surveyed different metals, okay, and he found, okay, copper was actually the best guy to form multi-carbon products from CO or CO2 reduction. Because the copper surface, by this is an intrinsic properties of copper, okay, it can absorb, okay, on the surface the CO molecule. And the important point is that the CO molecules can go to the surface and stay long enough to form a dimerization bond, and then you can make it can go to different intermediates and combine together to make different multi-carbon products. So on the other hand, if we consider like platinum or gold, for example, platinum absorb like too strongly the CO molecule. So it means the CO will just come to platinum surface and stay there, and it doesn't go away. So it means we have a things called poisoning effect, and we don't want that. On the other hand, other things like gold or silver is too weak to stay on the surface of the metal. So it means if you use gold or silver, you let CO2 or CO go to the surface, it just go away. So in fact, it is also very interesting because just if you replace CO by CO2, it means you use gold or silver for CO2 reductions, you will get a lot of CO. This is why actually if you for the even for the solid oxide electrochemical cell I mentioned before, people usually use silver catalyst to make CO. And if you check the literature, this field, you will see that mostly people work with silver catalyst for the CO. And also some other metal I can mention is that the bismuth or the tin are very good to make formic acid from CO2 reduction. But I will not mention about them here. Okay, back to the main things, the copper. Okay, it's this is good. Okay, then okay, you see by the CO dimerizations, it can form a different intermediates here, and those intermediates are very important to go to higher chain products. For example, you can have the different C3 intermediates as shown here, and those C3 intermediates were in fact modelized by DFT calculation, and also there are several report recently. Okay, they're trying to use spectroscopy to detect those intermediates to clarify. Okay, by which intermediates we can get which C3 products, because it is very, in fact, CO2 or CO reduction is very complicated reactions, since you have uh, lots of possibilities. I show you here C2 or C3 intermediates. They can form, like very different structure or molecule. But this is a very fundamental point of view, and there are a lot of ways, a lot of questions to answer here. Okay, um, okay, we know. Okay, copper-based catalyst is very nice to make multi-carbon products, but we need to know, okay, which copper and how to modify the copper, okay, to get the good product. So considering okay, the efficiency, which is also very important for the applications. Again, I have to emphasize this point. Okay, the progress here I just showed you some recent progresses for the productions of ethylene and n-propanol from this field of CO reduction. I need to mention again the importance of those two chemicals. Okay, the ethylene is in fact the most demanded chemical in the industry. Since you might know that, because ethylene we make like plenty of stuff. We can make polyethylene, we make ethylene oxide, a lot of things. Or even in some company they are trying to synthesize the fuel from ethylene as well, by you put ethylene and you do some conversion processes. Okay, and also n-propanol again is very important chemical as well, because you make it's solvent in the medicine or even in the industry and for a lot of stuff. But n-propanol is very, very difficult to synthesize, since it has three carbons again, and also the oxygen species inside make it very difficult to synthesize at high rate. Okay, and okay, to adapt with the industrial applications, there was some technical economics analysis showing that, okay, you need to achieve the reactions at least 0.1 ampere per square centimeter. This is the applied chronicity, okay? And the Faraday efficiency should be at least 70% for a product to make it practical. And also the durability of the system should be over 1,000 hours. And the last thing is that the total cell voltage should be lower than 3 volt to make it economical. But today I will just talk about the Faraday efficiency, and the other point. There are a lot of how to say, people trying to improve and optimize. Okay. Yes. Yeah. Also for ethylene. Okay. We were very interested in ethylene because in fact these projects was funded by Total Energy, which is a French chemical and petroleum companies. And in our lab, before we in 2019, okay, we had an idea to use a dendritic copper catalyst, and at that time we tried, okay, this dendritic copper, or DCU I show here. The DCU was very good to make the ethylene from CO2 conversion, which reaching like 40% as show. Yeah. And yeah, at the time it was quite impressive result because it was 2019. Okay, and this dendritic structure still we are trying to understand why it is particularly good for the ethylene. And and in the beginning of my PhD, like we were thinking like, okay, so why not using this dendritic copper for CO reductions? Because we are, let's say, okay, we were thinking like, okay, CO reduction could be easier than CO2. Okay, so yeah, when I came, I started to try. Okay, so how we made this catalyst? Okay, we very simple. Okay, so we perform a method called electrochemical reduction. So basically, we just put a copper plate into the solution of copper sulfate with different acid concentration. Okay, so when we apply the current density to this, okay, the copper sulfate will be reduced into metallic copper. And at the same time, we have the hydrogen evolution reactions, which make a lot of hydrogen bubble on the surface of the copper plate. Okay, so it means, okay, this we can control the porosity and the dendritic growth of this catalyst. Okay, and okay, beside, okay, and then we can just scratch the electrode to obtain the copper powder. Okay, and then okay, we can perform the calcination in air to vary the oxidation state of copper, because uh, copper can has three different states: zero, one plus, or two plus, and each oxidation state can affect the selectivity of the reactions. Okay, so after getting this powder, so I just perform the drop casting method onto the gas diffusion layer, which is called GDL here. The things I just showed you before, and then just put it to the flow cell. Okay, so now I go to the activity. So firstly, we survey the dendritic copper synthesized by different acidic concentration. I'll show here. Just sorry. I should have shown you this as well. By morphology, you can see that okay, even going to higher calcination temperature, the dendritic structure was always maintained. Except that okay, the primary particles slightly change, which also makes sense because this is very usual in the inorganic material. When you perform calcination, you have different uh, morphology edge, different particle. Okay, okay, the activity. Yeah, now I go to activity. You see that okay, the sample synthesized. We found actually we found that the dendritic copper synthesized with 2 molar sulfuric acid was the best one, and we could even reach it to like 70% efficiency. Okay, and yeah, we survey at three different current density from 0.1 to 0.2 ampere per square centimeter, and we compare the sample okay calcite at different temperature, and we found that okay the sample uh, calcite for 400 or 500 was slightly better in terms of ethylene compared to the non-calcite sample. Okay, but the drawback of those guys that if you go to higher current density, you see that much hydrogen was evolved, and we got less the ethylene. So therefore, we decided to stick with the sample without calcinations. Yeah, even though this current density is not the highest one, but we also need to compromise it with the efficiency, and still it's acceptable. Okay, and yeah, we also perform the optimization by the electrolyte concentration. Oh yeah, I have to mention that the electrolyte concentration is also a very important thing in this field, because the several studies show that okay, the concentration of the cations, which is can be either potassium or cesium or sodium, can affect significantly the selectivity of the reactions. And we found that, okay, we from 1 to 7 molar of KOH, the 3 molar was the best one to get the efficiency of 76% of ethylene productions in terms of frag efficiency. And then we perform the long-term electrolysis to know if the system is stable or not. And it showed that, okay, it is quite okay. Over 8 hours, we can get almost like 80% frag efficiency for ethylene, and even C2 plus products, we get like more than 90% of frag efficiency. And I have to say that, okay, this result significantly highlight the importance of CO reductions over CO2 reductions. Since by CO2 reduction, you can get plenty of products like formic acid, CO, or methane, which means like a very large part of your current density or your electrons will go into CO products, and then we have to think about the way to extract them and then make them more useful later on. But on CO, okay, we just primarily get the C2 plus product, and we don't get any C1 products in this case. Okay, and then back then, oh yeah, we were thinking like, okay, let's make a comparison between CO and CO2 reduction by this catalyst. Okay, and then we utilize this guy directly for CO2 reduction to see, okay, imagine if these guys can also make very good ethylene from CO2 reduction, and in this flow cell, okay, so it will be even very better. But okay, we found that, okay, by CO2 reductions, in fact, the efficiency for ethylene was much lower, just around 40%, and we got more hydrogen in this case as well. So yeah, this is also again highlight the difference between these two reactions and using this catalyst. And yeah, so these results was in fact was conducted during the first year of my PhD, and it was very interesting collaborations with Total Energy. And then yeah, we continue the collaborations. We think about other directions. So okay, ethylene was very good as well, but how about n-propanol and ethanol? Those alcohol are very important and very difficult to make as well. So we think about the way to synthesize them. So basing on the previous report, okay, so in our lab, we had before the things called copper NC. So what it is, this is in fact the single atoms of nitrogen, carbon, and this make a network, and then you put the copper onto it. Okay, it was also a work of one of the postdoc in my lab before, uh, and in this case, the valence of copper was like copper 1 plus, and this compound was very good to make ethanol. But the thing is that, okay, the important point here is also the nitrogen, the presence of nitrogen doping as a heteroatom was very significant to get the ethanol here. And besides, several studies before by a different group showing that, okay, by using the method doping like silver or gold, they could achieve very good efficiency for propanol. Okay, so we were thinking like, okay, how about just combining these two things together? Okay, let's try. Okay, imagine you put together the metal doping and the nitrogen into copper. It's possible to achieve more alcohol or not. Okay, so we have to find a way to make this possible. Okay, and yeah, the way here is that we firstly, we start with the commercial nanoparticle of copper from sigma and trig, okay, and then we perform galvanic exchange reactions. We can perform with silver or gold, okay, or do two step. Firstly, gold and then silver, just to try. Okay, you can do a lot of things here to try which combination is the best one. And okay, then you can get the things going. Okay, the trimetallic, which contains silver and gold doped into copper, and then you perform the oxidation or calcination in order to convert all of this copper into copper two oxide. Okay, and then you perform the nitridation process, which means you mix with sodium nitride inside autoclave, and you perform the heating process, and over 20 hours you can dope nitrogen into copper. Okay, and all of these copper oxide would be converted into copper nitride, and with the presence of gold and silver doping as well. All these materials start to look very complicated. Yeah, back then I had a slide before. I should have shown. In fact, it was also one of our first result to try to survey, okay, the effect of nitrogen and metal doping and all together. Oh, so let's just start with, okay, the basic things. Is this the common nanoparticle from sigma and trig? Okay, so in this case, you get mostly ethylene. Okay, like more more or less like 50%. Perfect. See, no, yeah, I just, yeah, 50%, true. And you see that, okay, let's try, okay, how about just make nitrogen doping into this without any metal doping? But you see, we had a slight improvement in terms of in terms of n-propanol here, like just few percent of being improvement. In the case of solely metal doping, you get much less uh, n-propanol, which is quite unexpected, but it is a result anyway. But important point. So when we combine the nitrogen and the metal doping all together, you see that, okay, the efficiency for n-propanol were significantly improved, like up to 30% at this current density. Okay, 150 milliampere per square centimeter. So this result inspires to try more with other metal doping. So we also tried gold and also palladium. So we found, okay, silver and gold were very good to make n-propanol. So this was in fact our first result. This was in I remember it was in the second year of my PhD. Okay, so we found, okay, they are very good. So this is why we make gold and silver together with copper, but not just only one metal. Okay, and yeah, the characterizations of the trimetallic compound with nitrogen was very, I would say, very intense. We employed the HRTM and we found that, okay, the presence of gold was like the nanoparticle on this in the material. It looked like this, okay, and even by EDX we found that, okay, gold was kind of localized. On the other hand, silver was like more homogeneous on the whole material surface. Okay, this is the TM, okay. But then we also brought this sample to synchrotron, the exact analysis. By the way, I was just talking with Chandong about the synchrotron in Thailand. This is in fact very good chance or very nice idea to think about it later. But here, in this case, in the framework of total energy, we did it in the Soleil synchrotron in Paris. Okay, and found that in our material. Okay, uh, at least firstly we look at the copper edge, and the copper was mainly present as copper nitride, as I'm showing here. Okay, when we perform, like the measurement for also for the reference sample. Okay, for the gold edge, what we observed was also mostly the gold bonding as shown here. So this is also confirmed why we got the nanoparticle gold in our sample. But on the other hand, okay, for silver it was very interesting. We found a shift in the nitride sample, and it's very interesting as you see here. So the sample without nitridations, had this silver as it looked like only the silver bonding. But with the nitridation, we see that copper and silver was actually bonded together. It's make copper silver bond, which is also explain why we had a structure like the silver was kind of isolated atoms, and on the other hand, gold was like nanoparticle. So this result was confirmed by both EXAF and EDX and TEM. And of course, the activity can be the most important things as well. Okay. Firstly, we survey the sample with only one dope, 1 meter dope. When we found that in any case, the efficiency for alcohol, C2 plus alcohol, including ethanol and propanol, in any case, was just around 60% as shown here. Okay. And the lowest case was like 40%. But then, if we combine all together in a variety, the content of the metal, so we could boost the alcohol production rate up to like 76% as shown here. This condition optimized as 1% gold and 0% atomic percent of silver. So this took a lot of times and work to select the ratio and for activity measurement as well. So then we decided to stick with this sample to do further characterizations and activity optimization. And yes, again, we also performed the electrolyte concentration shown here. And the best one was like with 1 mole of KOH, as shown like 76% of C2 plus alcohol shown here. And yeah, we performed the reactions for like over 12 hours when we found the system is somewhat stable over these conditions. Okay, of course you might have the variations of the two alcohol over time. Okay, but yeah, normally they are quite persistent. Okay, and then we have to know the how to characterize the material before and after electrolysis, and also we perform the in situ characterization to know the status of our material. Okay, and we are very lucky we collaborated with Professor Jean-Marie Tarascon, who is actually I think is one of the most famous expert in the field of battery research at Collège de France. And we collaborated with his group to perform the in-situ XRD measurement. And we found, that our sample during electrolysis will contain metallic copper, silver, and gold. And also this result was double checked and confirmed with the in situ XAF here as well. And then with this, so why we decided to take these result for DFT calculations. Okay, why? Because we need to know the state of the copper. We go on to know which items and which oxidative state should be put into the DFT. And yeah, for the DFT, we collaborated with a guy in Total Energy, Guillermo, and the first thing he did was he figured out the possible elementary step for the mechanism of CO reduction into C3 plus, sorry, yeah, C3 plus intermediates, which are important to make n-propanol. Okay, and yeah, the things he has done was like to compare the energy, free energy of those reactions over the surface of the bare copper, and also the silver copper or silver gold copper derived from the nitride material. And he found that in all cases it's actually easier with the metal doping compared to the bare surface of copper. And this result is actually also very consistent with the previous literature. Okay, and yeah, and we also perform some post electrolysis characterization. We calculate the coordination number of the copper in our system. Okay, and we found the sample during the electrolysis has lower coordination number, and basing on some previous literature, we they did. In fact, they performed some fundamental study like by spectroscopy, even though it was not really, not really optimized yet. But they gave an idea that the lower coordination number of copper during electrolysis could enhance the C1 C2 coupling reactions, which is important to make the C3 products better. Okay. And also, another thing is we performed measurement of electrochemical active surface area, and we found the sample during the sample with the electrolysis show much higher ECSI as shown here, and so confirmed by the TM observation. We found the grain boundaries density of the sample after electrolysis was much better, and these results also, like in some previous literature, they show this can boost the formation of oxygenate products, which is important to make alcohol. Okay, and this result, in fact, at the time of publication, was also the highest value of frag efficiency for ethanol and propanol altogether from CO reduction, with almost like 76% of efficiency. The so this is the things we made at Collège de France, for the in terms of the catalyst, but we also had some collaboration with other groups in France to try different nice idea. So one of the thing recently we did was like, let's just think about the material origin. So usually, in the chemical industry, well, what we get, where we get the copper is actually from the mine, like process like here, show here. But the mining process can be very polluted. Like everyone here know about that. But how about like using the plant to make the catalyst? Oh, that sounds very I don't know. That sound can be very unusual. Okay, but the thing is that some plant can have a strong absorption of the heavy metal in the soil or wastewater. So this is why, thanks to the idea of Professor Claude Guizot in Montpellier. She's a very good friend of my boss, Professor Mafuntaka. Anyway, and in her group, they focus on different bio-derived material. So they use this plant, they plant this plant and they put them into the wastewater and try to see if those plants can absorb any heavy metal and a good amount or not. So they employ different things. I don't know, but maybe this plant is also very popular in Thailand. I think because I'm from Vietnam, but I have seen it a lot in Vietnam as well. Coffee powder, everyone knows about that as well. And she found that especially the coffee powder was very good to absorb copper from wastewater, and the method she used was like called bioabsorption. And she found coffee powder was very good to absorb copper, and of course you might have a different trace metal other things. Yeah, and he different plan. Okay, and she found this, and then she gave the sample to us, and we try. Okay, so this is very interesting. Is that the coffee powder sample gave a very good efficiency for C2 plus product from CO2 reductions. Okay. Ah, in this case, we only tried CO2 reduction because this is how to say very original and very big elementary research. So we just tried CO2 reduction instead of CO. We might try CO reduction later. Okay, so coffee powder was the best one, but let's among the plan. Okay, but when we compare even this coffee powder with the commercial catalyst, the nominal particle of copper or copper oxide, and this shows a almost very comparable result compared to the commercial ones. Then we also performed the long-term CO2 electrolysis for this sample. It was pretty okay over a long time. So this suggests that okay, the copper catalyst even made by the bioabsorbents from copper waste uh, can be very very potential, and we might think about the let's say the new way to synthesize different material from okay the waste, and which is can be more environmentally friendly for the industry as well. Okay, so this is all the things I would like to introduce to you guys today. And yeah, I uh, cannot forget to thank Collège de France, especially Professor Martin de Cap and Dr. Tran, who were my supervisor, and now they are my director. And of course, all of the people participated in my research before, and also Total Energy. Thanks for their financial support. And again, thanks Shannon and for inviting me here, and also everyone here for listening to me. And I'm happy to answer any question.
Yeah,
Thanks.
it's my
Yeah.
pleasure to have you here, and I believe we have lost touch after Japan, but yeah, now we're
Yeah.
back, and looking at
Yes.
your work is very, very impressive. And
Thank you.
if I have to summarize, I think this is a very cool approach to look at the practical way to utilize carbon dioxide.
Yeah.
And other people are working on carbon dioxide reduction, but you took a different approach by doing electrochemical CO, carbon monoxide
Yeah.
reduction.
Yeah.
And that gives very good result. And I have to emphasize that all of these results are done at the industrially relevant current, so more than zero point 0.1 amp per square centimeter. So that's very impressive because me myself, I only work with 1 or 2 or maybe 10 milliamp per square centimeter. So that's like a magnitude lower than what Hong is doing. And yeah, let me start with my question. So you work with pure CO, right?
Yeah. Yeah.
Meaning that you assume that the CO2 get reduced first by the solid oxide electrolysis to CO,
Yeah.
and then you use
Yeah.
that CO. But have you ever done using like a syngas or CO or less concentration of CO? Because right now I think you use like 100% CO putting in
Yeah.
your flow cell.
Mm. Exactly. This is one of the things. In fact, we got this question when we make the patent. In fact, because the patent officer, they are actually also the scientists, and they ask us because it's maybe even closer to the actual industrial conditions, because you cannot always get the pure CO for sure. And yes, very interesting. And we are trying to work on it. In fact, even in my lab, they are the people who work on the diluted CO2 for now. But for the CO, since okay, we are now just still at the very beginning step of the research, and we want to understand, like have a very clear point of view about the mechanism and the way to make the products from CO. And then, okay, so once we get, very good and very clear enough point of view, and then we might try to, to add more things into the CO fluid. Yeah,
Is
try
there
to
any
see even the
is there
mixture of
any
CO2 and CO. Yeah.
is there any safety protocol for the CO
Ah,
experiment in your lab?
very, very good questions. Yeah, I get this question all the time. So
Mm,
what we need to do, we put everything inside the film hood, okay? Even the gas chromatography and the cell, okay? And we always have a detector CO with in, in our lab coat and also in front of the window of the film hood.
mm,
And the uh, detectivity of the detector is like even like 1 ppm or something, so which is even below the gas exhaust from the car or the motorbike. Okay, so that's just to tell you how we
okay.
are.
My next question is how. Yeah, that's good to know that you have the safety protocol. Otherwise, I would be worried because you're working really with a very high concentration of CO. My
You're right.
next question is, how do you fix your catalyst on your gas diffusion electrode? Do you use any binder?
Yeah, we use Nafion and also
I see.
sustain ion sometimes.
Hmm.
You can try many things. But by the way, just to mention that it is very how to say, I don't know if it's a good decision of European Union or not. But since 2 years ago, they banned the Nafion. You might know it. Okay, so now we cannot order Nafion anymore from any European companies. So in fact, I had to order it from Japan.
Mm,
Okay,
yeah,
the
I order
sustain
it
ion
from
is still
China.
okay.
Yeah, I know.
Okay. Okay.
Quite sad to see it's being fade away,
Yeah, yeah,
phased out.
no.
Okay, next question is how do we how does your experiment setup look like? How do you characterize all your product? Because you mentioned you have liquid product, you have gaseous
Yeah.
product. How do you measure all of them? What kind of
Oh,
machine apparatus do you use?
yes, a very important question, of course. For the gas product, we use the online gas chromatography, okay? And we use things, okay, for the, for the multi-carbon products in gas phase, we use the FID detector. And for hydrogen and nitrogen oxygen, UTCD, okay? And of course, we also have the mixture of industrial gas to calibrate the GC. This is why we can obtain a good concentration and result. And for the liquid products, we use enema. Okay,
Mm.
since almost all of our products are like protons product, we use protons enema. Okay,
Okay, cool. We have two questions from the audience.
yeah,
Um,
okay.
you can read it and answer it, so I don't have to read.
Uh, the chat. Okay, fine. First one is from Firalang. Okay. For high current density, I observe overload current density, probably due to low ion transfer. On the map, is there any other reasons overload current from ionic conductivity? Okay, let's just think about overload current. You mean the if I might understand well, your questions is mean you see the drop of selectivity at high current density. For example, in the case of dendritic copper catalyst, I would think about the membrane as well, but in our opinion, we thought about is like the most important thing could be about the intrinsic property of the catalyst
I
itself.
think what she means is
Yeah.
that for her H cell, the
Ah,
nephron membrane cannot keep up with the high current density. Like, how do you solve this problem in your flow cell? Or the
so
cation exchange membrane cannot keep up with 1 milliamp or 0.5 milliamp. How can you solve that?
I see now. Okay, if I to be honest, if you work with H cell, this is the how to say the strong drawback of H cells. because okay, you don't have basically you don't have a support of kinetic in the S cells. You just steer the electrolyte and let the electrolyte flow into the electrode. And this is why in the S cell, usually I see the result is only a 20 or 10 milliampere. But in case of flow cell, you don't have to do that because in flow cell, again, you have the triple phase boundary again. So I think this is the key point. This is not because of the membrane, because even in flow cell, we can use Nafion or Carrier membrane as well. Yeah. So yeah, so I think this thing is again, this is just due to the cell configuration. Okay, I hope it's answer well your questions. Otherwise, you can always send me a private message. I have two part question from Jos. Is there any corrosion effect like carbon corrosion or hydrogen in Britain possible to happen to water catalyst? If so, how does it happen? Oh, very good questions. Carbon corrosion. We haven't observed any carbon corrosion in cascade of CO reduction yet, since the CO is very inert in electrolyte. So imagine if you just flow the CO continuously into it, nothing will happen. A hydrogen in Britain, okay, since the efficiency for hydrogen is very small in this case, so and also the hydrogen will just once it's produced, it just go through the gas line and go to the GC, and there's no accumulation of hydrogen in this case. So not for the moment. Yeah. Okay. And when you tested Zans, how did you build the cell for the testing? How it was the cell? Oh, very good questions. For the in-situ Zans, okay, we use a specific cell design at the beamline of the French synchrotron. And how was the tick of the cell? Oh, in fact, I just gave the sample to the supervisor, and he came to the synchrotron. So I don't know about the cell, but to have an idea, I seen another cell at another beamline also at the same synchrotron, and I could estimate the thickness was like let me try to think about it, like below 10 centimeter. Okay, that's what I remember from you. But in our case, okay, the flow cell we use in the lab, the thickness is like 7 or 6 centimeter. Okay, in the total.
Do you have more questions sent directly to you, or these are all the questions? I guess these are all the questions. Hong,
Okay,
you
I
have more
guess.
questions.
Yeah.
You mentioned there were some questions sent directly to you, right? Or not?
No,
Okay.
I don't think so. Yeah, it's fine.
All right,
Yeah.
then let's conclude this um webinar. Thank you very much, Dr. Phong, for spending your, I guess, evening with us. And
This is lunchtime now.
oh,
In fact,
lunchtime, right?
okay, it's okay. Yeah.
Lunchtime with us.
Uh,
So yeah, thank you very much for your time. And if you have any questions, feel free to reach out to Dr. Phong, or you can contact me. And we have this kind of webinar running every 2 weeks. So the next one will be coming out soon, and all the exciting stuff, including batteries and also hydrogen and other things. Um, so yeah, to end the webinar, can we ask some of you who are willing to turn on your camera, and we take a nice selfie together? Is that all right? If you can, please, yeah, turn on your camera. You want to go back to maybe your highlight slide?
mm,
Which
what
slide
was
would you like to
that?
show in the screenshot?
I have to share again, maybe.
No, it's okay. We
Uh,
can still see your screen.
oh, really? Okay.
Yeah.
trying to see the
I see
this
some of my students there. Good. They join.
it's like
All right.
check attendance of the lecturer.
Yeah, that's okay. We can take photo with this slide. Okay.
Okay, good. And
All
yeah,
right.
in fact, this is a very how to say good chance for me to see the students are motivated for the research. Yeah,
Mhm.
when
Yeah,
it
come
reminds
back
me
to
a lot.
Southeast Asia. Maybe you will find many talented students.
Yeah,
Yeah,
for sure. I mean,
don't stay in France for too long. All right,
Thailand
let's
is
take a
very good.
nice
I mean,
selfie.
yeah.
3, 2, 1. Okay, one more. All right. 3, 2, 1. Okay, thank you very much.
Yeah.
Bye bye, everyone.